For the past 5 years, Shimadzu has been telling you about our new and innovative technologies to address metabolite ID, accurate mass, innovative software to enhance your workflow. I thought this year we'd take a step back and readdress what some of the early stages of mass spec looked like and try to redefine the wheel a little bit. What you're looking at here is the new classic single quad, the very definition of the easiest mass spec we've ever worked with. And I'd like to tell you a little bit more about why we've reinvented the wheel. Over the past several years, certainly it's no secret that we've been talking about faster chromatography, smaller particle sizes, higher pressures. The idea being, let's get our peaks out in a smaller amount of time, conserve some solvent, conserve some resources. The big thing that's gone along with that is we've been looking at higher end mass spectrometers, and as you've heard from another of my colleagues here today, we haven't been able to keep up in the high-end mass specs. They just aren't fast enough to keep up with those chromatographies. And if they're not fast enough, our single quads certainly are not. What we've done is to reinvent that. We have a new mass spec that now scans at 15,000 AMU per second. The closest thing on the market to it right now is 10,000. It can do polarity switching in 15 milliseconds, whereas its closest competitor is about 10. And it has an extremely high sensitivity of 350 to 1 signal-to-noise ratio on a picogram of reserpine on column. Why do we want that? Well, it's all about quantitative points on a peak, preserving the ability and the integrity of our quantitative measurements. To get good quantitative data, we estimate somewhere between 10 and 20 points to define a total ion chromatograph peak is required. If you get less than that, you start having trouble defining the peak and the peak shape, and as we all know, TIC is not as uniformly distributed as something like a UV. It's a point-to-point connection. So we need that higher scan speed to be able to get those peaks and create the quality that we need. One of the things you think about when you think about increasing speed, one of the nasty side effects that comes with it is a loss of sensitivity. And we think about that when I'm scanning at 15,000 AMU per second. If I translate that, it means I'm scanning or dwelling for about 66 microseconds on every mass that I'm analyzing. And if you briefly consider that a quadrupole is actually a time of flight region, the amount of time we're dwelling is less than the amount of time it takes something that's even 100 m/z to cross that quad. That's why we lose sensitivity. What we've done is to change the way we apply voltages to the quads to get rid of that loss of sensitivity. What you're looking at here for bisphenol A and estradiol is what you'd observe for those two compounds on a normal quadrupole as you increase scan speed. It's an incredible loss of sensitivity. What we've done is our new novel approach here, and I can't describe it in too much detail, but rest assured that we have equalized that out so that no matter what scan speed you're moving at, your mass spec will not suffer any losses in the data that it produces. Finally, we're looking at that polarity switching speed. Here's our previous model, LCMS. You see about a 400 millisecond switching time with a pretty nasty voltage display looking at the high energy voltage converter on the mass spec. Versus what it is now in 2020. It shows 15 milliseconds. I'd argue with the spacing here that it's probably more like 5 milliseconds. I'm not really sure how much more stability you're going to get in that last 2 blocks or the 10 milliseconds there. So it is a very, very fast switching system. I told you about the sensitivity. Here's replicate analysis 6 times showing over 350 to 1 for that 1 picogram of reserpine on column. The spec on it is 150. That's done by an RMS method. Quite simply, it is the world's best single quad, but who needs it? We all know that drug discovery is lined up with walk-up access systems. Almost all of them are single quadrupole mass specs, confirming synthetic products. They're easy to use, they're robust, they're easy to maintain. I would argue that there's another group that really does need them, and that's your core mass spec facilities. If you are in a core mass spec group, you've invested a lot of money in a very high-end mass spec. You know that you can't have a lot of them, but human nature tells us that as soon as a really high-end mass spec shows up in the group, nobody wants to use anything else. And part of the problem that goes along with that is if in their own group all they have is an LC with a PDA or a UV, the conditions for the chromatography that they've worked out for their separation back in their lab is not directly transferable to LCMS on their high-res instruments, or any mass spec for that matter. For that reason, it would be really nice to have a very fast scanning, very robust screening tool in front of your lab. So your chemists can walk in, do all of their method development on a single quad and transfer it over to your Orbitrap or your ITTOF or your QTOF or whatever instrument you have later on, rather than creating a backlog in doing all of their method development on your really expensive system. Finally, we have minimized the downtime of an instrument. Two of the big things that happen in LCMS is you clog the ESI pipe and you clog the desolvation line or the inlet to the mass spec. ESI pipe on this instrument can be replaced without taking apart the probe. It's just a peak fitting and it's finger tight. Also, the desolvation line into the mass spec can be replaced while the instrument is still under vacuum. No need to vent it to replace that line. 15-minute operation and you're back up and running. Like I said, it's simply the world's best quad. We're ready to prove it. We hope you'll give us that opportunity. Thank you for your time.